So first up, we have Theresa Roelke. Her research focuses on providing individual patient care, and she manages patients in the Maine Medical Center Lung Screening Clinic. She was awarded the ACCC 2020 Innovation Award for her work on the 3D Nodule Tool. The tool is featured in the current March-April issue of Oncology Issues. Theresa is developing an additional educational tools to support patient education and understanding of lung health, including a lung cancer screening shared decision-making patient video and phone app called the Tobacco Leaf app to track on individuals' daily smoking and low-dose CT findings, as well as support quitting, all within the context of lung screening. Next up after Theresa, we have Michael Lane, who is the director of the University of Vermont's IMF Labs and the Technical Services Partnership, which is a provider of comprehensive healthcare technology management for clients' biomedical and lab equipment. He holds a bachelor's degree from UVM in biomedical engineering and a master's in business administration. Michael is a member of the American Society for Quality with a CMOQE certification, the American Association for Medical Instrumentation, and the Healthcare Information and Management Systems Society. Last up on our speaker docket today, we have Scott Tighe, who is currently a senior researcher and technical lead of the UVM Integrative Genomic Facility, which handles advanced genomic analyses for the University of Vermont and our associated institutes. His expertise is all areas of genomics, including next-gen and Sanger sequencing, microarray PCR, single-cell analysis, flow cytometry, optics, and experimental design. Scott is a microbiologist by training, with a strong background in microbial detection and bioaerosols. So those will be our speakers today. We look forward to their talks. I do have one quick housekeeping rule to help us stay on time. Dr. Jessica Heath and I will be moderating the questions today. So if you have questions throughout the talks, please submit those through the chat box feature and we'll make sure that those get asked. So with that, I'd like to welcome our first speaker, Theresa Roelke. Thank you.
Hi there. So lovely sunny day to be presenting the UV Lathe. I'll start with this and we'll talk about the Nodule Tool later. The UV Lathe is a portable system designed to inactivate viral particles on N95 masks for reuse by the original user. Next slide, please. So the situation we're well aware of, we're in the midst of a global pandemic. Depending upon location, there does continue to be limited and unreliable supply of PPEs and specifically FFRs by clinicians, personnel, fire departments, etc. But this is particularly true in rural parts of the US and around the globe. Next slide, please. So proposal is to build an automated system to inactivate viral particles on N95 masks. The project received funding from MTI and matching funding from the MaineHealth Innovation Center to build the first prototype we call the UV Lathe. Lathe means to bathe or wash. And again, mentioned earlier, the system is meant to be to inactivate viral particles so that the mask can be reused. So the aim in part is to demonstrate the use of UVC light and that it is effective at inactivating viral particles on FFRs. Next slide, please. So the team, we have Tom Lamontagne from Lamontagne Engineering. He's a mechanical engineer who helped design and build the first prototype. We have research validation done by Dale Syphers from Bowdoin College, a physicist there, and then also Jim Vaughn from UNE. Next slide. Oh, and we also have marketing from New Frontiers Management Group. Next slide, please. So the purpose of the lathe, mentioned earlier, inactivate viral loads on certain FFRs so that we can reuse the masks. And so not only inactivating the particles, but also thinking about how do we do it in such a way that minimizes the UV damage to mask head straps and nose pieces. It's meant to extend the life of the mask. It's meant to reduce cost over time, conserve resources, and reduce waste. We'll go on and move to the next slide, and we will let, I'm not sure what that one is. Tom, take over. Go ahead, Tom.
Yep. Thanks, Lisa. So I'm Tom. I did the mechanical design and prototype build of the lathe.
There we go.
Yep. So the whole design started with this fantastic artwork by Dale Syphers, and he laid out the ideal placement of the light panels to ensure that the masks are uniformly irradiated by the light. And this layout required us to develop a unique system to adapt for masks of different shapes and sizes. So the result was a nice lightweight stackable aluminum chamber with adjustable light panels and an intuitive user interface. Operating the UV Lathe is like using a microwave. You open the door, insert your mask, and select your bake time. The interface contains presets for commonly used masks and filters and provides an option for users to create their own custom cycles. Now we have a quick video of how it works. And then with that, we'll turn it back over to Theresa.
Okay, so next slide. So komarebi is a Japanese word used to describe the beauty of sunlight as it filters through the forest in early morning or late afternoon. And so the trees and the plants on within the forest and on the forest floor will be exposed to direct and indirect UV light as it bounces off the surfaces of trees, plants, moss, dew, and it allows for the shadowed trees and the ground vegetation to have the opportunity to be exposed to and absorb UV light. So now we're going to go to Dale for the science.
So jumping off from that analogy with the forest, the filters in an N95 respirator have a bunch of fibers that have embedded charges that attract the viruses, and the light coming through is going to hit them either directly or indirectly through reflection. Next slide. So what we did was try to correlate the data on UV transmission through the mask and UV reflection through the mask and through each layer to correlate that with the UV exposure time necessary to deactivate the viruses. It turns out that the reflection is an incredibly important part of what goes on. Reflection values off the filters are between 20 and 80%. And it's the effect of multiple reflections that broadens the beam and allows the viruses that are attached in any shadow region to be hit by UV light and deactivated. Some of this data has been published with a researcher from the Food and Drug Administration. Next slide. So our tests on viral loads were deposited on the respirators in two ways: deposited on the outside of the respirator and deposited internally directly on the filter layer through an access slit. Both were exposed to UV light intensity for varying lengths of time, and we used the H1N1 virus as our virus tested. Similar size and reasonably similar construction to coronavirus. For the surface deposition, greater than 99% of the viral load deactivated in 3 seconds of UV LAVE exposure, and between 40 and 60 seconds for no detectable viral load. That's up to log 5 in the 3M masks. For an internal deposition directly on the filter layer, very similar results, more than 99% deactivated in less than 10 seconds, and no detectable viral load in 60 seconds. And the slower deactivation rates are the result of the backward scattered light. Next person.
That's me. So who might be interested in using this LAVE? Rural clinicians, maybe throughout the country, since 90% of our country lives rurally. Long-term care facilities, funeral homes. I even thought, how about have it for use in the national stockpile? And so then we started to think about fire departments, police departments, and we ultimately decided our initial focus would be with EMS. And so we're scheduled to actually present this LAVE to Portland EMS and the EMS directors within the region during their upcoming leadership meeting. Next slide, please. And so who else? then we thought, how about International Red Cross EMS? And so this article, or there was an article, there's a link to it there that was from the BBC about 4 weeks ago, and talked about Red Cross EMS in Tijuana, Mexico, population 2 million. They often refer to the city with that has a double pandemic, so gun violence by night, COVID by day. They had 12 ambulances to serve 2 million people. And so I started thinking, well, could this be used by the Red Cross and maybe somehow put it into the cabin of their units, of their ambulance for use. And I did connect with the executive director, Andy Carey of Tijuana Red Cross, to see if there might be some interest in this, in the LAVE. Next slide, please. So basically just, thinking about the LAVE to help support populations across the globe who may be struggling with limited resources, and specifically N95 masks. Next slide, please. And I just want to close with saying the fundamental purpose of clinical innovation is to create experiential learning and get the tools into the hands of the end user so that we can then think about maybe researching and understanding, learning more, and really also understanding the impact that the innovation has. Thanks for your attention.
Great, thank you, Theresa, Dale, and Mike. I was just wondering quickly, you had mentioned that you were hoping to minimize damage to the mask. Did you all test if there was any damage that occurred over multiple go-throughs with the UV Lathe?
So I'm familiar with the work that has been done on damage and reuse of the various masks done by others. And the construction of this was such that the amount that of the UV light that comes in towards the foam layers around the nose is 2/3 of what comes from the other direction. And that maximizes the ability to deactivate the viruses and minimizes the amount that hits the foam nose piece. When I take the amount that hits the foam nose piece and correlate it with the other studies, we end up finding we can reuse masks between 15 and 25 times.
Yeah.
Great. If there are any questions, please submit them through the chat box. Just as a reminder, if there are no other questions, we can continue on. Charlie Irving would like to know what the next steps are with this technology.
So the next step is to, start to get the unit out there. We have the prototype, we want to make more, but we also want to gauge interest, and then we thought, let's start with EMS. So I did, that sounds like the EMS locally around Portland, they're very interested in this. And so we're in the midst of scheduling, introductions to it through presentations. But then I keep thinking, not just in the States, but far beyond the States. Think about the amount of people who live global, around the country and the world who live rurally. And so this is something that really, it's a countertop unit. It can be put in multiple places and used, in a variety of settings. And so the next step is to kind of work with the EMS, see what we learn, and then go from there, and then really think about larger volume manufacturing. And it looks like we've got another question.
I saw the questions. I would add that we're also looking at a wide range of masks, not just the 3M. We're also looking at the ENVO mask, which is used by EMS people, and looking at the filters of those and a number of other masks. And so there's going to be some more research on those, broadening it out. The viral tests were done by Jim Vaughn at the University of New England. He's a virologist, and I'm a physicist. He that the concentration per 50 milliliters has controls, and then we subject them to the UV light for varying durations, and then he cultures them and looks at the amount that are deactivated.
And we're trying to get people to embrace this idea of UV light. It really is effective. It's been used for a very, very long time. And it's funny that, you know, people are still apprehensive, and so this is showing, yeah, this actually, there's science behind this. It works and it's effective. So, yeah.
Do you want to address the commercialization plans at all, Theresa?
In what way, besides just the early on? What were you thinking, Dale?
Have you,
How to get it out there. The challenge is just really, you know, again, trying to work with new frontiers and, you know, just trying to make people aware of it. And that's why my thinking is just start with EMS, see what we get for feedback, and then, you know, go from there, because it's so broad in terms of how this could be used.
you have a
That's what
patent?
we're trying to focus. That's what we're trying to focus on, you know, I think one step at a time. And this whole project has been one step at a time, like any other innovation. It follows the same path. The other things that I'm working on, I noticed, God, it's just funny how it just seems to follow a path. And yeah, we'd love to get it out there. I wish we could have gotten it out there sooner, but I just think it, you know, it takes time, and we definitely needed the science to validate use. I thought that was critical in the minds of all of us, I think, because we want people to trust it. So. You got one, Dale.
There's a couple of questions there. At what rate would the UV light deteriorate? I assume you mean the masks, and the rate looks like it might start failing form and function sometime around 25 to 30 uses.
Oh, we've got the stop
Stop
sign.
sign.
Thank you. So now on to the next one, a lung nodule patient education tool, which is part of a lung screening toolkit. Next slide, please. And so this is all about leveraging a 3D lung nodule educational tool to reduce distress that patients may feel around a lung nodule finding. And so the situation is that annually there's thousands of Americans who learn that they have pulmonary nodules, either through low-dose CT screening and within the context of lung screening, or just as an incidental finding on CT imaging. And so often patients have distress, they have fear, they're confused, and there may be a misconception between patients and providers. And the biggest thing is that they worry about the cancer risk that nodules may pose. And so this nodule tool uses the current technology, 3D printing, to explain lung nodules to patients when they're found. And this is, again, if we educate patients, then we can reduce anxiety. Next slide, please. And so this is just a little comic relief. Next slide. So this is the proposal, was to develop, distribute, and study 3D lung nodule tool to, again, increase patient understanding and reduce anxiety. So if you look on the left, that's the original tool. And that came from a closet in our thoracic oncology outpatient clinic. A nurse brought it to me and said, hey, I think you might be able to use these with patients who are trying to understand lung nodule size. And so this shows various diameters of lung nodules. So what I did is I felt that it needed to be more engaging in a visual way. And so I went on to design this tool. And so that's a visual of the first picture I put together of it. Next slide, please. And so then I went to work with took it to Mecca, worked with a Mecca art student, and we started to develop it further and 3D print it. So next slide, please. It shows the 3D printing process. And the next slide. And this is the initial prototyping. Next slide. I then took that initial prototyping. I surveyed 31 patients, brought it to clinic, did a shared decision-making consult with these patients, and I used the tool. And I asked patients, was it helpful? Did it help you understand lung nodules? Did you understand characteristics? Size was really important because patients don't often understand what a 3mm nodule looks like. They think it's giant because we're not a metric society. And so what happens is once they see how tiny it is, they're just like, is that all? You know, so that's very helpful. And then the other part that it was really important for me is because we're screening patients 55 to 80, I wanted them to be able to go home and be able to tell their family, you know, what the state of their lung health is. And if a nodule is found, what is the size? I want them to be able to have that knowledge to share. Next slide, please. Patient comments, picture's worth 1,000 words, was helpful. And so you can see here that it was quite helpful. And again, received a 9.4 overall satisfaction rating. Next slide, please. So then went on and felt, okay, we need to refine it a bit more and pretty it up. And so collaborated with USM MIST Lab in Portland to develop it further. And I worked with Jeremy Qualls, who's a dean there, to further develop it last summer. And so we go to the next slide and you can see the process here, and we move on to the next slide. And that's our final product so far. So second iteration. And you can see we, you know, came out pretty nice. It's pretty lightweight and easy to literally put in your pocket of a lab coat and walk into a room and have a consult with a patient and share this with them. And next slide, please. So mentioned earlier, it won 2020 Innovation Award. And then we go to the next slide. And so I did do a lot of presentations last fall on the tool because of that award. People were asking about it across the country, really, and especially lung screening programs. And so the other thing that's happening too is it's featured in the Oncology Issues March, April issue. So it's probably available right now to look at. There's an article about it. So we have 20 units, and what I'm hoping to do is make more, but we got to get the first 20 out there. And so I want to work with Tufts medical students, incoming students, spring 2021, to see if we can start to distribute it to clinicians and show them how to use it, and then have it available and get it into the hands of the end user, as I had said before in the prior presentation. I applied for a driven fund to manufacture, volume manufacturing, injection molding, in addition to 3D printing, so that possibly organizations can actually have their own logo on the tool, so they have a choice. Next slide, please. And so this is one of 3 tools that is under development, further development under the MaineHealth lung screening program. So the Nodule tool you now know about. The tobacco leaf app is to support quitting and track low-dose CT results within the context of lung screening. There's no app for quitting that is tied to lung screening, and I think it's really important because it helps patients take ownership of their lung health. Shared decision-making screening video to educate eligible patients on lung screening, encourage lung health stewardship, and bring screening closer to home to rural Mainers, because so many patients are tired of driving 2 hours for a 5-minute scan, and they tell me that all the time. And a lot of people don't have transportation readily available. So next slide. So again, I repeat, the fundamental purpose of clinical innovation is to create this experiential learning and get the tools that we're innovating into the hands of the end user, so that we can then further appreciate the impact of the innovation and study it so that we might be able to refine it further. And thanks for your attention.
Do we have any questions? I see that Charlie Irving has a colleague here at UVM who might be interested in this technology, if he'd like to comment on that.
Did you want, sorry?
Charlie,
are you asking me a question? Oh, Charlie?
No, I have a colleague here in pulmonary and critical care who's our local expert in CD detection of lung cancer. His name is Matt Kinsey. He has a grant from the NIH to do this. And I think he'd be interested, I suspect. So you might want to reach out to him.
Okay, yeah, I just wrote his name down.
Yeah.
Great,
the other person is Garth Garrison. Garth is really into teaching and education. He runs our pulmonary fellowship program. He might also be interested in several of the things that you're working on.
Great, okay. I feel like I know that name, but
This is
Yeah.
Gary. Teresa, actually, I had given you those names and you did make contact with
I
both.
thought so. I kept saying, was that way back when? So that was like almost 2 years ago. What we were trying to do is study the tool. And we were
Exactly.
trying to collaborate with University of Vermont and Southern Maine Health Center and Maine Med and get the tool out and study it between the 3 institutions. And, you know, we had a proposal, but, you know, it didn't work for whatever reason. And so, yeah, so I did connect with them and, you know, people were absolutely interested in the invite. And I was pretty excited, but it's okay. You know, this is a learning process and we'll figure it out. It'll get where it needs to be eventually.
The other group that I'm very active with is the American Lung Association.
Oh, yes. Yeah.
And they've made a big deal out of lung cancer screening over the last year or so. So that there's a guy there in Maine. Oh, it'll come to me. He used to run the ALA of Maine.
Okay.
He's in Portland. It'll come to me.
Yeah,
Anyway.
and you can feel free to send me any email, Charlie, you know, as far as any context.
Yep.
The other thing that I didn't mention is that USPS TF, it's hard to say on any day, but anyway, they had just set out new guidelines on the 9th, a couple of days ago. And what they're talking about is reducing the lung screening age to 50 instead of 55. And then reducing pack year history from 30 to 20. And so what they're expecting is that the amount of people eligible for a lung screening is going to double because of that. And so that's brand new and we have to wait for insurance, you know, to come on board, but I think that will happen. So we'll have more people eligible. So the tool, again, there's going to be more talk about lung nodules and how do we relay this information to patients in a way that feels not so threatening. So.
This is Gary. I have one quick question with regard to, so where we sit right now from the standpoint of patient physician interactions is a lot is being handled virtually. Have you compared the effectiveness of the tool, utilizing it virtually and utilizing it face-to-face in the same room?
So that's an awesome question. And I've done it. I've used it both ways. And so, because I've done like over 1,000 of these shared decision-making consults, probably closer to 1,500. But anyway, you know, I did use the tool in clinic and it was wonderful because they could engage in it. They had an experiential, you know, it was an experiential, you know, kind of knowledge. And so they were able to touch it and hold it and so on. And then as far as I have used it virtually, I've held it up. And patients loved it. And I said, do you see it? And yeah, no problem. And they understood it. So you can do it both ways. Thank you.
So I'll get started. My name is Mike Lane. I'm the director of IMF Labs and Technical Services Partnership here at the University of Vermont. And my topic today is around the Vermontilator, which is a rapid cycle design, build, and FDA approval initiative by UVM. So just a brief role here. So IMF here at UVM was established in 1967. We're located in Burlington, and we provide the research community and the Vermont business community with a place to apply and develop prototypes. And we have a full design and prototyping facility here at UVM. There's a wide variety of activities that we're focused on, whether it's mechanical systems, fabrication of parts, or electrical mechanical systems, and the types of materials and so forth that we work on are pretty widespread as well. So in this particular project, it started with Dr. Jason Bates, who's a professor of medicine and pulmonary and critical care division here at UVM, molecular physiology and biophysics, electrical and biomedical engineering, and the graduate coordinator for bioengineering. Within our shop, we have 3 research engineers that this is their full-time job in terms of developing prototypes based on the research here at UVM. And the driver for our product, the Vermontilator, obviously was related to COVID and the dramatic impact that we were seeing in a very short period of time. What happened was really an overnight change. So on March 17th, one of our research engineers was conversing in regards to ventilators and the shortage of ventilators that we were going to see in the marketplace at the time, and asked about reaching out to Dr. Bates, who we've worked on a number of different projects with. At the time, that initial email generated a prototype, which I'll show you here shortly, within about a day and a half. We directly contacted our UVM innovations group here in terms of IP and the innovation. And then we engaged the Vermont Manufacturing Extension Center, Vermont manufacturers, and a group called Quality Matters to focus on the FDA aspects of the project. So it was a very rapid cycle here. And then towards the end of that 2-week period, we also engaged the UVM MBA program here to work on some of the business aspects of the Vermontilator. So specifically in regards to the ventilation aspects, the particular mode of ventilation that the Vermontilator focuses on is Aprv, which begins with a pressure higher than the baseline pressure and follows a short deflation. And it alternates over a cycle of time. Basically, in this graph that you see here, very high pressure for a longer duration, short duration for a low pressure. So the overnight, basically Dr. Bates sent an email with a diagram that you see on the left here. Basically, this is a cylindrical rotating disc with a small hole here that represents that time duration, that short time duration of pressure. And from there, one of the research engineers took stock of some of the materials that we had in the shop here and created this device that you see on the right here. And this glove represents the lung, and you'll see a circle as we demonstrate this that is rotating, and ultimately the glove inflates. So from there, we took and we identified specific sets of parts that were needed, and the device that you see here, obviously a lot more went into the design and the specific bill of materials. We've got a full function ventilator tester here that we're measuring actually the flow pressures and so forth on this unit. And this is a fake lung on the left here. From there, we actually worked with a number of Vermont manufacturers to, again, the focus was on delivering this as a low cost mode of ventilation for Aprv specifically. And we worked with a number of Vermont manufacturers to work on different aspects of this this product. And this is the final design. You'll also note that we worked with a software engineer to build in a number of different alarm faults and signals here. There's a number of different modes in terms of breath periods and a data connection, which allows us to output waveforms. So this was the production model that we built, and we've got a total of five of these units over the course of the past number of months. One of the things that was a challenge during this time period was over that 2-week period, we were also moving everybody to remote work, with the exception of the individuals that were working in our machine shop. One individual remained in the machine shop, another had a home machine shop and was doing some of the work there. And then we were doing remote work with our vendor partners as well. Also during that time, we found that in Vermont, there are definitely some challenges related to reliable internet. We were changing meeting software, cameras, new voice over IP system. All of this transpired during that 2-week time period. And what we were doing was we were meeting on a daily basis, Saturdays and Sundays included, walking through all of the details of this product. The innovations and the changes were happening really overnight. We would make particular changes and designs, and then the next day build those out and bring those forward. And coupled with this, we were working with individual called Quality Matters to focus on the FDA emergency use application process. And we did submit an emergency use application to that, and had a number of meetings with the FDA. Coupled with that, obviously there was a Defense Production Act, which moved forward a ton of money into the ventilator production. And I'll talk a little bit about kind of the next steps that we see with the Vermontilator. But we did have a number of meetings with the FDA and put that package together. We also worked with the UVM innovations team here in terms of intellectual property, planning for licensing. There were a number of conversations with international connections, both in Africa, Ecuador, and other countries as well, talking about our short and long-term plans for the device. And as I mentioned, we engaged a number of students in the MBA program who did a comprehensive international review. We're looking at the different regulatory and accreditation reviews that would make sense for the development, and also worked on the website as well. The Vermont Manufacturing Extension Center that we engaged helped function as project managers, identifying specific roles that manufacturers within the state of Vermont could play, brought those resources to bear, and we were able to engage a number of them in terms of developing and producing key parts to the 5 production units that we have. There were particular roles that were identified for different manufacturing partners. We've got 3 that were identified, some that were producing the stainless steel shell, the rotating disc, and also would function as the primary manufacturer. We went through and developed a comprehensive bill of materials. Again, the goal was to really make it simple and inexpensive, and also make sure that it was easy to repair. That meant making sure that the parts were readily available, and that's why you'll find that in the design, the computer system actually, or the alarm system actually functions as a standalone from the rotating disc. We are measuring the pressures and so forth, but if that, for some reason, that fails, the unit would continue to function. We also did a number of tests for the unit. We completely and totally mapped out the output testing, pressure and flow, and got detailed runtimes on that for essentially a multi-day period of time. we were doing water intrusion tests, strain relief tests, and we also contracted with a company here in Vermont that did electromagnetic interference testing on the unit as well. There were an incredible number of people that were involved with this endeavor. The core team, obviously led by Dr. Bates, myself, and the research engineers here. But we had engineering initiatives from a number of folks, including Just Fire Tech, NRG. A number of UVM grad students helped with some of the software design. On the clinical side, there were a number of colleagues that provided input and insight, came down and did some reviews, and we actually brought it to the hospital and did some testing there in terms of one of the lab setups. Regulatory, we had some input and assistance there from a great group. IP, the UVM innovations team. Manufacturing, as I said, VMEC was extremely helpful in all the partners that they brought in. And then the MBA students participated and did a lot of research and so forth as well on the project. So it was really an incredible collaborative effort in a very short period of time. Kind of the next steps that we see, as I mentioned, the product, we did submit an EUA on that, but at the same time, the environment changed in that there are now thousands of ventilators here, specifically in the US market. And we've had a number of conversations in terms of developing countries and so forth. And our goal is to actually extend this from a single mode of ventilation, Aprv, to a more all-purpose ventilator. And we're working right now on that strategy as we move forward. So, and just Nancy McGregor was also a member of that team as well. So again, in a very short period of time, this was basically a 1.5 day initiative, moved to this product within a couple of weeks, and then by the end of June and early July, this is where we were at, and working on the next phases of the project. So with that, I'll be happy to take any questions that folks may have.
Got any questions for Mike? Thank you, Mike. I have to say, this is Scott Tighe over in the Genomics lab, and we've been using the services over at IMF, and you guys are absolutely amazing. I can't believe the talent that you guys have over there. I just appreciate you guys now that I've been using you guys. So
thank you, Scott. Appreciate that very much.
Okay, I'm going to get started here. I'm going to kind of change gears away from innovations a little bit to more of what we've been doing over the past year over here in the Genomic Center at UVM. I am Scott Tighe, and I am the technical lead over here and director of the technical director of the Genomic Center. So we've been pretty busy. Let me see if I can figure out how to advance these slides. Yeah, so for the past year, actually, we've been doing COVID testing over here in the Genomic Center. We set up the lab in February, started testing in March, and during the shutdown, we maintained 2 people in the lab over here. We were actually part of 3 international consortium, which is the GLAMP, that's a global LAMP consortium, and then the MetaCode, which is an international metagenomics for testing for COVID, as well as for sewage. And that's over 400 people in about 30 countries. So it's a pretty big group. We did all the testing for Jet Propulsion Lab up here before they launched the Mars 2020 rover. because we are one of the few labs that were open and doing it. We had a couple of publications. We also have 2 more going in to press here in the next week. So we've been pretty busy. There's also a group through ABRF where we started this working group down here where you can go to WhatsApp, and it's a place where you can ask questions, post answers, see every technical manual and manuscript that's been written. There's been over 5,000 posts on that. So I'm actually one of the leads on that as well. So we've been really busy over the past number of 11, 12 months. Little overview of SARS. CoV-2, 100 nanometer virus. I'm displaying some of the functional proteins that you see on the outside of the virus here. Although because we're a genomic center, we're not after these types of protein, but you do get an idea of how many copies of these particular ultrastructures are out there. So it's a positive stranded, single stranded virus, RNA, and it's 29,900 base pairs of RNA with a 33 base pair poly-A tail. And this varies a little bit from strain to strain, but generally speaking, this is the Wuhan strain. That's this 947.3 is the actual strain in NCBI that I get this data from. So the important part here to realize is that how many viral particles is in certain parts of the body. So we all started going after the nasal for NP swabs because we were 10 to the 6th, 10 to the 9th, and the throat had about a log lower, and sputum was highly variable, but still a good target. But people did do NP swabs and still do NP swabs. And stool, of course, has about 100 times less, but that comes later after you're infected and you start shedding the virus. But nonetheless, we find it in sewage all the time. So just you've probably been hearing a lot of this on the news for the past 10 months, probably too much of it. But so some of the things that we do in the lab is Rtq Pcr, digital PCR, RT lamp, which is loop mediated isothermal amplification, which is incredibly powerful. And then of course we do variant sequencing because we are a next-gen sequencing center. And most of what we're doing is environmental surveillance. And at the very beginning, we started in clinical because we work with the hospital to set up their testing. But right now there's 177 EUAs right now for nucleic acid testing. And that's kind of a lot if you think about it. And TaqPath is probably the most popular, with N1 and N2 being the 2 primers that we use to actually tag and amplify the neocapsid gene of the virus. And we do that in the lab. That later evolved to NEB Luna assay, which is a little bit higher sensitivity and a bit more efficient. And that later evolved even more to a better test, which is the TaqPath combo, which uses it and spike protein and open reading frame. So there's 3 multiplex primers that we could go after for the TaqPath combo. And this is one that you hear a little bit about, the S dropout. So we can actually hear and detect and then sequence this UK variant. So digital PCR I wanted to highlight because it's actually my favorite way to actually detect COVID, and this was an instrument that was bought by the CTR. So we put this tool into very good use. So this is a really good opportunity for me to explain what we're doing with it. And there's 2 EUAs on that, and that's the Bio-Rad QX200 that you guys actually helped us purchase. And then RT lamp, I'll go over that. And then variant sequencing, which is something that we just set up about a month ago. So this is the genome. The genome's 29,000 bases, and you can actually see there's 10 open reading frames with sub reading frames in here. And what I'm showing here in red, this is where we actually tag, we do PCR. These are the primer sets for the N2, N3, and N1 gene that people are using. Right now, UVM is using N2 through the Broad. All the samples are just amplified with N2, not N1 and N3. N3 was the original primer that got dumped 8, 9 months ago. Nobody uses anymore. So Broad uses N2. Our lab uses N1 and N2. And then the new TaqPath combo actually added open reading frame 1AB and then the spike protein that people are talking a bit more about. And then the RT lamp, which I'll talk to you about, is actually tagging the envelope protein and then in the N gene as well. Our variant sequencing is an Amplicon protocol, and we have upwards of 100 primer sets that are going to cover this entire genome or transcriptome, if you will, and to sequence that. So we're using what's called the Arctic protocol that uses 98 primers, and I'll show you a little bit about that in just a minute. So Rtq Pcr, N1 and N2, I don't want to get too deep into the weeds here, but there were two methods that I mentioned. One was the Luna and one was the original Thermo. And the reason Luna was created, if these are regular Rtq Pcr curves, these are supposed to be exponential. And if you look at the N2 gene, this is not an exponential curve. And the reason is because the TMs of the actual PCR thermocycling was 10 degrees off from the primers. So that's why we switched over for NASA over to Luna, and that became a very popular assay, and people started doing it as a routine assay. And you can see when you use Luna master mixes, these are more traditional amplification curves that look exponential. So we moved on to this after we kind of put this one on hold. It just didn't look as well, and NASA wanted to use this. Nonetheless, I have to say, all of these generate, people ask this all the time, they generate false negatives. They generate false positives. This is the nature of the beast. Nothing is perfect, although qPCR is very sensitive, as you all know. And I'm having a little bit of time driving this screen here. So then it got improved. The DetectPath combo came out. And like I said, there's 100 tests or more of this, but they added a multiplex multicolor Rtq Pcr that could detect this S dropout. It's highly sensitive. State of Vermont uses this, which is fantastic in case you start seeing positives somewhere else. You could actually try and get it done at the state of Vermont because it's so sensitive. But you can actually see here's the S gene. It's just a cartoon, but what I'm pointing out here is that this is a forward primer and this is a reverse primer. What happens is because there are SNP sites and deletions in this particular area where the probe's supposed to sit, it doesn't bind. So you get this S dropout. You don't see the S, but you have the open reading frame comes up positive and the N gene comes up positive. And then if you sequence that, you can see that is missing here because of that deletion. What's going on here? Digital PCR. This is a molecular counter. So if people in Maine haven't taken advantage of this, it's open to you guys to use. You just have to let us know. What it does is it takes the PCR reaction and it segments all the molecules into their own emulsion beads. And then we do miniature PCR reactions, upwards of 100,000. And each bead would contain one DNA or one RNA molecule in the case of COVID. And we do an amplification. And then the machine is actually just a flow cytometer that counts as positive and negative beads. So you can actually see here, down below that EW1, 2, and 3, we actually had 17,000 negative bead counts and we had 0 for this sample. And then we actually had 6 counts that were positive here. And likewise with this. So this is the counts of SARS-CoV-2 per 5 microliters RNA. And these are discrete molecular counts. No standard curve needed like you would normally use with a qPCR reaction. LAMP is called loop-mediated isothermal amplification. So this is just simply colorimetric. You add RNA to it and you incubate it at 65 degrees. You can also monitor this LAMP color by using qPCR, but just as a fluorescent monitor. I'm not going to get into LAMP, but it does use 6 primer sets, which makes it extremely sensitive, and it amplifies at 1 temperature, so it makes it very easy to use in restricted situations. And this is just a LAMP panel that we did on some wastewater testing some months back for NASA. So variant testing, I'll just move on to that. There are 3 types of variant sequencing that are happening now. Some labs are just doing direct RNA sequence of a pool. You extract RNA and you just RNA sequence everything that's in there. That's one way to do it. Or you go into what's called capture, bait, and capture. You go in and actually fish out the pieces by hybridization and then sequence those pieces. Or you can do amplicon. We chose to do amplicon because it's fast and it's economical. And we use Illumina sequencing, but you can do nanopore sequencing. And we're using the Arctic V3 protocol. And it's really robust. It works quite fantastic in our hands. But it really is restricted to CT values below 33. So you need to have at least 1,000 copies there to get good sequence and full coverage. We sequenced the 200,000 to 500,000 reads with paired end sequencing with the Illumina platform. Of course, if you want to do higher CT values, you'll have to sequence a lot deeper. And you can see a map down here where I have a read plot where you have half the amount and then a full amount of the reads where you start losing coverage across the genome. So this is 0 megabases to 29,000. And this is how we're describing the variants, right? Like B117 and B1351 and 614. And this is just a report that gets kicked out depending on how you do it. Our bioinformatics group does the bioinformatics, and we can tell you your clade and your strain if you want to do that. We're working with the hospital right now. We have this little working group and with the state and the hospital. So we're all driving forward so we can actually do a lot more strain sequencing. So I'm going to actually leave it there because we're out of time and take questions if there are any. Gives us 4 minutes. I like to finish early.
Hey Scott, this is Jess Crothers. Question for you. So have you been just sequencing a portion of the genome looking for variants as opposed to doing the whole genome?
No, actually, if we're going to do it, we'll take RNA and just sequence the entire thing.
Okay.
Although you bring up a point, right? There are methods where you can just sequence S, the spike protein open reading frame, but it's so much easier just to sequence the whole strain. It takes it's like an 8-hour prep. So.
That's what I thought. I think I misinterpreted your last slide. I thought you were saying that you were just looking at certain portions.
Hey Scott, great presentation. With respect to that sequencing, are they, how are they proceeding with the diagnostics? Are they cherry picking some samples to look for strands here and there, or is this a routine process that's done when people test positive?
Yeah, so the recommendations right now vary from state to state and actually country to country. But right now it's 3 to 5% of all positives below 32 CT are recommended or mandated to be sequenced depending on what state you're in. So in Vermont, that's not a lot, right? Because if we're getting 200 positives a day, there's probably only, and Jessica Crothers can comment on this, but there's probably only maybe 30 or 40% of those below 32. So it ends up being not sequenced. 3% of that is probably only like 2 a day.
Okay.
Am I right on that, Jess?
Well, I'm trying to do your proportion of the CTs, but I mean, I think we're at like 130 a day. I've worked it out to be like 900 positives a week. And currently there are like 14 are being sequenced a week, and that I've worked out to be like 1.5%. And so we're getting there. We're not at the 3 to 5%. And to your question, Seth, we're trying. Like there are multiple kind of wheels turning to get to that, but we're not there yet.
And one of the things is the question still remains based on epi. Is it 3% or 5% of positives below a CT of 32? That's the big question that's still up in the air, and I think epi's still working out. Maybe you or Christine know the answer to that. I see she's on the Zoom.
I haven't heard the final ruling, and I think the CT below 32 comes into play with what you can actually sequence, right? If the CT is too high, there's just not enough virus to sequence. Is my understanding, it wasn't that we're concerned about old infection or duration of infection at that point in time. It was really, what's feasible. And again, there are multiple different pathways in which this is happening. So the state is taking 14 and sending them to Massachusetts Department of Health. Nikki Sideropoulos is working on a kit here at UVM just to try it out. And then Scott, you guys are doing a whole different process. So there's multiple different avenues. So maybe if we add them all up, we're getting close, but I don't think it's definitely has not been a fully coordinated effort yet.
Actually, now it is. So we meet every week.
Yeah, now it is.
Right now. So the hospital, I think Diane's on too, but the hospital in my lab, we do the same thing. just because we had to, and we had been doing it for a while already. So nobody wanted to reinvent the wheel. But yeah, so we're gung ho and all coordinated now, Christine.
Yeah, it was a bit of a monkey show before.
And I will say one last comment is that, there's a lot of discussion about sequencing wastewater, and it's not as straightforward as WCAX makes it out to be, because you only get pieces and parts of the RNA when you come through wastewater. Wastewater is better sequenced by doing bait and capture, which is like a 3-day protocol. But nonetheless, you can't call full variants from wastewater because the RNA is so degraded. So I wish it was as simple as the news makes it out to be, but it certainly isn't.
And the
All
last
right.
thing maybe I would say to Seth's comment too is that, this is really in the realm of epi and understanding the dynamics of tracking variants at this point. And we're not at a place yet where we really know the clinical implication of these things. So it's not really a diagnostic test yet as far as managing people in a medical way. Maybe that'll change, but we're not there yet.
Well, it sounds like there's some opportunity to make some innovative changes to how this kind of testing is done, Scott.
Well, there are a lot of people working on it, Charlie. There's all these consortiums, and I probably had about 60 emails this morning. So we actually created an entire new test here over the past 6 months, Charlie, where we actually did what's called length ratio analysis by LAMP, and we called it long LAMP. So we actually measure the viral integrity before we try to assess it from something like wastewater or some place where it could be degraded from, because as you know, qPCR, the targets are only 67 base pairs. So you can degrade this virus beyond belief and you can still detect it. So if you actually have a ratio to say we're going to compare the 67 to 100 to 300 to 800 to 1,000, which we're doing now at this long LAMP, we can actually make some inference on the condition of the actual virus. And I think that was a missing piece. So we're just wrapping that up and sending in a manuscript now. But and I believe that the FDA has stopped they are recommending to stop all EUAs for testing, and they want people to just focus on what we've got for tests and move forward. So I hear.
Yeah. One of my fellows that works in Seattle has been working with the ID Now folks at Abbott.
Oh, yeah, and there's another group that has an electronic device that we're sending up to the International Space Station to do this, and it's an electronic LAMP biochip. So it's just everybody's got a new invention every time you turn around. So any variants found so far from so.
Can you answer this super quick, Scott, because we need to wrap this up.
Yeah, we can wrap it up right now. I will say everything's a variant. And I would never reveal that over a Zoom call because all variants have to be handled kind of carefully before people talk about it.
All right, great. Thanks, Scott. Thank you to all the speakers today and for everybody for attending. Have a great day.